Hello, today I will show you our new velocity controller, Trapezoid Velocity Control Model. The previous time we were having some problems with the joints were oscillating after the 10 degrees per second velocities, but we managed to solve this problem, which drastically increased the robustness of the controller. So we will start with showing some. We will just move each joint one by one, and then later I will just send random positions to show how good or bad our model is working right now, and we will see. Okay, let's start with the joints one by one and move the first joint to the 15 degrees by just a slow speed, like 5 degrees per second. So we see that it's completed in almost 3 seconds, which is very nice, because let's stop this and look at it. As you can see, it's just started at almost 1 second and it's completed at 4. So for the first joint we can go back to 0 degrees to see again. Okay, I sent it with 10 degrees per second, so it should be around 1.5 seconds. So it started at exactly 1 almost and completed a little bit after the 2.5. So it should be 1.5, so the total should be around 2.5, but it's just exceeding it a bit, like 2.6 right now. Okay, we will send it to a bit further now with to the 45 degrees with 15 degrees per second, which should make in 3 seconds, and we will see. Okay, let's stop it and see. As you can see, we went there almost, so finished a bit for 5 seconds, so it should be around here 3 seconds, so it's around 0.1 seconds more than it should be. But obviously we are just not taking into account that we are accelerating and decelerating. We are just saying that if we want to go from 0 to 45 degrees with 15 degrees per second, it should be 3 seconds the total time. But obviously this is when you are moving with the constant velocity. But right now we have obviously the acceleration and the deceleration parts, which were missing the previous time. So these increase the robustness and decrease the oscillations. As you can see, there's almost no oscillation at all. This is causing because of the starting, but as you can see, it's not repeating, so it's pretty nice. Let's put the joint 1 back to the 0. This time I will send a really high speed to show you something. So I'm sending from 45 degrees to 0 degrees with 45 degrees per second. As you can see, we almost had really a glimpse of the constant velocity, but since the total distance was equal to the speed, so 45 degrees distance, and it should be completing in 1 second, but let's see how long it takes. So it started almost before 2 seconds, so it should be 1.9, and completed in almost 8, we can say, I think. So it's like 1.9 seconds. So it should be 1 second, but it's completing in 2 seconds. That's happening because we are not reaching the constant velocity. We don't have time for that. We are sending to the 45 degrees distance with the 45 degrees per second. So our controller doesn't have enough time to reach the constant velocity area. So it's just accelerating and starts to accelerate. 0.8 radian is I think almost the 315 divided by 4 is like yeah, it's almost reached the limit. So this is as we can see, this is the very short time of the 45 degrees in radians, 0.8 in the in the clockwise direction. So let's now go with the second joint to 0 degrees. The second joint is carrying the weight of the other joints. So as you can see, it's rotating around the z-axis. So if you move it too quickly or with a high velocity, that it may cause oscillation. So I will just start with slow speeds like 5 degrees. So it started from minus 45 degrees and reached to the 0 at, so let's see, it should be almost 13, sorry, 14, 9, no, sorry. It should be 9 seconds. Let's see how long it take. Yeah, we can see it's almost took 9 seconds, maybe a bit more than 9 seconds. So let's send it back to the minus 45 where it was at the beginning with the 15 degrees per second. So it should complete it in 3 seconds. So it's here 2 seconds and a bit more. So yeah, it's almost, we can say maybe it's just okay, it's easier to see here. It's started after 1, a bit after 1, and we can say 1.1, and it stopped at 4.3. So it's completed in 3.2 seconds, something like that. So it's pretty nice. So let's go with the third to go with the 15 degrees with only 5 degrees to see how it's doing with these small speeds. So as expected, it's completing in 3 seconds. Now let's go to the minus 15, which makes the total distance with 13 degrees and with the 15 degree seconds. So it should complete in 2 seconds and see. So it started almost 0.75. We can see it make a little oscillation here at the beginning, was not repeating, so it's okay. So 0.75 to 325 is almost 2.5 seconds. Our expectation was 2 seconds, so it's just almost 20-25% difference. Let's try it again to go to the 15 degrees, this time with 10, so it should be 3 seconds. Let's see how it reacts. As you can see, it's now decreased, the error decreased a bit, so we can say that it's just working good. At least we don't have any oscillations. So I'm just sending it back to the 0 degrees. So with the fourth joint, I will go first to minus 90 degrees. So I will go back to minus 35 where we were with the speed of only a 5 I will give, so it should take 9 seconds. As far as I can see, it started around 63, so now plus 9 is makes 72, so it's just exceeding a bit. But as I mentioned, that the 4th and the 2nd joints are just carrying the weight of the others, so they are a bit prone to oscillations, especially when they are starting, because they are just acting against the gravitational forces also. So I will just make sure that the robot is in the starting position. Now the fifth joint is moving to 15 degrees with 5 degrees per second. Should be completing in 3 seconds. Yeah, it's almost started 1.5 seconds, completed in 4.5 seconds, so it's 3 seconds is okay. So we will go with the minus 15, so it's total distance of 30 degrees, so I will go with the 10. So it should complete in 3 seconds. As you can see, there's a little oscillation. It's just completely ignorable. We should be completing in 3 seconds because the total distance is 30 and the speed was 10 degrees per second. So we can see that it's just exceeding it like 0.2, maybe even less seconds, so it's pretty on time, we can say, I think. So the sixth joint is let's see, I think it's at 45 degrees at the beginning, so I will just this minus 45 then it should be. Let's see. Yes, the sixth joint is starting from the 90 degrees, so we will go to 75 degrees slowly with the 5 degrees per second, so we should be completing in 3 seconds. Let's see, it started at 1 exactly, so we should be completing in 4, almost 3 seconds, it's just very sharp. 2, we are going back to 90 degrees, with this time 10, so it should be completing in 1.5 seconds. Let's see what's going on. Yes, it's almost 1.5 seconds. It started 1:25 and finished 2:75-ish, so it is good. Let's try the last joint, 7th joint, with this one is in the 45 degrees, so it should be going to the 30 degrees with 5. So it should be completing in 3 seconds. As you can see, it's completed in just exactly 3 seconds. Going 45 to with 15, so we should be completing in 1 second, but obviously it won't. So it's exceeded a bit more than as expected, because as I told, that when the velocity is getting closer to the distance has to be traveled, the timings are not getting as expected, and this is very normal since the acceleration and the deceleration parts are getting increasing, and we are not getting into the constant velocity area that long. So as you can see, the biggest part is of the travel of the joint has happened in the acceleration and deceleration part, or maybe at least the 50%, so it's normal. Now I will just send it randomly. So if we look at the teleop command, we can see that our random position is the 30 degrees from the starting position, so it can be anything between the minus 30 to 30 plus the current position. So it's just, if the first joint is at 0 degrees right now, it can go from minus 30 to 30 with the speeds changing from 0 to 15. So it means that our one of the joints, or more than one joint, can be stopping totally, not moving at all. So let's try sending some random positions. As you can see, it didn't have any speed or position change for the first joint. Let's try it again. I have to remind you that we are not checking collisions, but the FCI is checking. So if our command is causing a collision, that the FCI will throw an error and just avoid the collision. So we are not worrying about the collision, but it can just it doesn't mean that we are also controlling. So it's just, we are doing only the joint position control, not checking it. And with the last command, with the teleop command, is a reading from the file. So my file has a point of this. So these are the speeds. So we can just change the degree of the joint and the speed, the velocity of the joint from the text. So I will just send it and to see what's going on. Okay, as I told you, it's not checking the collision, so it's working fine at the beginning, but not random position. I will try to send it when it's done. I'm sending it again to see what's going on. As you can see, it's just stuck. I will just restart it while we are waiting. Alright, I just changed our command to a safe position so we won't get stuck. Now I will send the command. So as you can see, each joint is following its own order. They are not working together, they are just working separately, but at the end they are just making the final pause all together. As you can see, our main problem was oscillation, especially at the end, because the joints were, if they were faster than 10 degrees per second, they were passing the goal position and trying to just converge to the goal position, but they were just keep passing, and and it starts to oscillate, and after a while we had to stop by the hand. So we fixed that problem. Now with the Trapezoid Velocity Control Model, it's now working in the manner of time, and the velocity is working really well. But obviously it's not checking if there is a collision or not. This is not a path planning or inverse kinematics calculation. This is directly joint control. So sometimes, as you've seen, it's getting stuck. Thank you for watching. See you next video.